this is the work we were doing with the vibration absorber. And to get started, just as a review, I would like to do a 1 degree of freedom system. Which is shown up here in the initial diagram, where you have a 1 degree of freedom mass. A real simple problem, just hanging from a ceiling or a fixed support. It has an externally applied force on it right here, and you can draw the free body diagram of the device, which is shown here, and then from that free body diagram it would be very easy to come up with the equations of motion, which are shown here. Notice that it is 1 degree of freedom, so you would expect one differential equation, which is what you have, using one motion variable, which is the x1 variable, and it's second order. It's second order because you have kinetic energy being stored in the mass, and you have potential energy being stored in the spring. In addition to that, you should be able to take this relatively simple differential equation, put it into the standard form, which would look like this: x1 dot plus 2c omega n x dot plus omega n squared x, and read off the natural frequency. So in this case, it's very simple to find that the natural frequency is k1 over m1. Okay, so at this point, I'd like to pause the recording and take a look at the solution of this with Mathematica. So, okay, here is the Mathematica solution of the equation, and I've edited it a little bit so it looks a little bit different perhaps. But here is the original differential equation. We have a constant input, and we have a oscillatory input, and I'm simply solving the equation. So here's the solution to the equation, and what you should notice is that there are some constant terms in here, right here for example, and essentially this is going to simplify with the denominator. But anyway, notice that there are some constant terms. That is coming from the constant that you apply. In addition, the constant term has the natural frequency, or excuse me, the forcing term. No, I'm sorry. It does have the natural frequency, which is omega 1. The oscillatory input has a component here which has the natural frequency in it, and it also has a frequency from the forcing term itself. Okay, so all I did here was I just simply cut and pasted essentially the solution from above, so I can make things a little easier. And then what I'm doing is I'm plotting the solution for a couple of different values of the constant forcing term and the oscillatory term. So in the first plot right here is the solution if the the constant is 1 and the oscillatory magnitude is 1. And notice that what's happening is you have at least 2 frequencies. They're actually exactly 2 frequencies, because you've got these large humps that are occurring less frequently than you have these smaller humps. So what's happening is you have a mixture, just like you have in the equation up here, you have a mixture of frequencies that are occurring in this. That's because you have part of the transient and the steady state solutions that are kind of mixing together. If you drop out the constant forcing term, then you'll end up with this plot here, and notice that it's symmetrical about the y-axis because you don't have any constant offset to it. So you might kind of anticipate or expect these kinds of solutions. The other thing that would be instrumental to take a look at, I guess, would be to change this frequency so that the natural frequency becomes equal to the forcing frequency. So if you did, we'll just simply make the forcing frequency equal to the natural and execute these. And what have I done? I've done something wrong. I don't know what I did. Let me pause it and figure it out. Okay, basically what was happening is I have a singularity when you hit exactly the natural frequency. So what I've done is I've put in a number that's pretty doggone close to 1 for the frequency, the forcing frequency, so that it can avoid taking 1 over 0 and then crashing. So anyway, if you execute those, you end up with these plots. So this one here is the plot when your constant forcing term is equal to a 1, and you have a natural or forcing frequency, which is pretty close to the natural. I mean, you can see what's happening. It's growing as time goes by, which you would probably expect. And essentially what happens is when you excite a system at its natural frequency, it tends to pump energy into the system. So if you're looking to get energy into something, then you go up to excite it at a natural frequency if it has one. And then down here is the plot when you leave out the constant term. You can see that the second plot with 0 constant is symmetrical about the axis. So anyway, this is essentially what happens when you hit the natural frequency. If you want to look at the steady state values, then what you can do is put in a little bit of damping. So down here what I've done is I've modified the original differential equation, and I've just added a tiny amount of damping to the equation. Damping tends to move things and make things look strange, and so what I want to do is be able to allow the system to reach steady state so that we can take a look at what it looks like when it gets there. So I've just added a little bit of damping, but I didn't want it to mess up, in a sense, the solution. So I've added a tiny amount of damping. We'll go ahead and solve that equation, and what I'm doing here is just writing down the steady state solution that I get from the previous one. And so we'll execute that. So what happens is now this is a plot, and it'll be the plot that occurs at steady state. And the reason for that is if you look at the differential equation, the time constant is about 2,000 seconds. So I'm plotting from 8,000 4 time constants, from 4 time constants to 4 time constants plus about 30 seconds. So I'm making the same plots that I did above. This time I'm looking at, or hoping to look at, the steady state. So here's the steady state solutions. If you notice here, you don't see that you don't see any evidence of 2 frequencies, and that's because when you hit steady state, the transient is gone. So just to show you that, what I'll do is I'll change this base time that I'm plotting. So now I'm going to plot from 0 to 30 and re-execute. And here we go. And you can see there's clear evidence that you have 2 frequencies in there, and that's because you're at the transient period. If you make this, say, 100, the base time, plot it again. Well, maybe that's not enough, but let's do it, say, 1,000. what eventually happens is you begin to see that the transient is disappearing or getting smaller and smaller, whereas the steady state kind of remains the way it was before. So I think you can see that those secondary humps, the frequency of the natural, are kind of disappearing. And this is being run where the forcing term is half of what the natural frequency is. If you were to run it at a higher than natural, so we'll change the natural frequency 3 halves, so it's going to be higher than the other. You'll see these humps coming from the forcing term to be quicker than the transients. Okay, so there we go, and then we can put it back to about 4 time constants, which is about 8,000, if I remember right. And at that point, then your transient is essentially gone, and you have nothing but what appears to be the forcing term. So that I think demonstrates the other. So let's put in this case, omega equals 3 halves. Actually, let's put it back the way it was. So we put in 1 half as the frequencies. So this is below the natural frequency, and we're looking at the steady state. Let's take a look at the one that's symmetrical. It's easier to kind of see what I want to show you. I'm going to right click on this and pull up the coordinate values. So I'm going to just kind of hover over this peak, if I can find it closely. So the peak is about 1.3. There we go, about 1.31. And then the low peak, it should be symmetrical. So if I can get a hold of it, well, anyway, it's hard to navigate with this mouse. But anyway, it's symmetrical. So the lower peak is about 1.3. So what I'm going to do then is just simply take the initial transfer function, the one that does not have damping, and or excuse me, I'm going to get the solve for the transfer function. So I replace all of the derivatives with s, just like before. I solve for the output over the input. So the transfer function, the output equals input over 1 minus 1 plus s squared. And so the transfer function is, if you divide by input, you get the transfer function to be. It's fairly simple. Then what I want to do is find the steady state response. So what I do is I take the transfer function and I substitute in s equals I omega. Omega is the forcing frequency. That's the frequency that I'm going to shake it at. I've taught you in class how to find this by hand, but what we're going to do here is just ask the Mathematica to tell us how big is this transfer function at W. So I just ask for the absolute value of it, and I ask for this percent mark means the previous result is what I want you to use. And so what it does is it puts in omega equal 1/2 into the previous result. And so here's the solutions. Here's the original transfer function when I substitute in s equals I omega, and then I simply ask for the absolute value of it, and this is what the absolute value is, and then I ask for it as a number when you plug in omega equal 1/2, and it's 4/3. So what it's telling me is at steady state, this solution will have a magnitude of 1.3, and that's what we saw up here on the graph. When I pull up the coordinates and you hover up here, and it's 1.3, close enough, 1.324. If I could hover the mouse a little closer, I'd end up finding out it was really a 1.33. Okay, so hopefully this shows you that there is a relationship between the response of the system, which is shown in the graph, and the magnitude that you can calculate from here. You can also calculate angles of these transfer functions. So, for example, the sine wave of the input begins with, because it's the sine, it would begin at 0, but this output is going to be shifted slightly from the other. You can see where the magnitude, where the response comes off. It's not at the origin like you might expect. Okay, so let's move forward. There's a couple of references here that I'm going to show YouTube videos of things that are happening. So at this point, what I'm going to do is go back to the iPad and continue there and show what happens when you put on a vibration absorber. Okay, so we're back here to the work that we had before, and so now what the vibration absorber does is it hangs another mass right here on the previous mass, so it doesn't really change anything in the previous problem. All it does is add on another mass with a spring to the original structure. So now this will be a 2-degree of freedom system. It happens to be 4th order because you're storing energy in mass 1, kinetic in mass 2, potential in spring 1, and potential in spring 2. So now that you have 2 masses, you draw 2 free body diagrams. So you have this one, which is slightly different from the original, and you have this new free body diagram for the absorber mass that you've attached to it. Over here you have your 2 equations that you would expect because it's 2 degrees of freedom. So you would expect 2 differential equations, which is what I have. And you can see, hopefully you can see that these equations come straight off of the free body diagrams. Okay, so this is the equations that govern the absorber problem. Unfortunately, had a little bit of a technical glitch and lost the iPad connection, but I'm back. Let's take a look at these equations and try to solve them in Mathematica. As I was saying before the glitch, unfortunately you can't really look at these equations and use the simplified standard form of the equation to identify what the natural frequencies are. So it's a little bit more complex. But anyway, we'll come over here to Mathematica, and now what we'll do is we will have these 2 equations. Let's see, I can find my bearings. Okay, so we'll carry on here. In this case, I'm going to let K2 be 1/4. So if you notice, it's less stiff than the original spring, and I'm going to choose mass 2 to equal K2. So if you had only the equations for the absorber, in other words, you just ignore the fact that it's attached to mass 1, but if you have a spring and a mass of the absorber, and you size it, that is what I'm doing here, I'm sizing the absorber so that the natural frequency of the absorber all by itself is equal to the original natural frequency of the system it was attached to. Because if you remember, we chose K1 and M1 to be 1, and so that gave us a natural frequency of the original structure equal to 1. And that's what I'm doing here. I'm attaching a spring, a mass of the absorber so that it has the same natural frequency as the original one, but it's smaller because the mass is smaller than the original, and the stiffness of the spring is smaller or less stiff than the original. So everything is a little bit less. In this case, I'm going to allow to have a little bit of friction, or damping, excuse me. So I've thrown in a damping coefficient. Right now we're going to let it be 0. And I'm going to ignore the constant force. We're just going to let the oscillating force equal a magnitude equal to 1. Right? So what we do is solve these 2 equations. So here we have the original, or the first equation, and we have the second with its initial conditions, and then we have the second equation as well. They're coming off of the iPad diagram, and it has initial conditions of 0. Just to keep things simple, we keep the initial condition 0. And all I'm going to do is, in this case, to do a numerical solution to the values. That's why I've defined the values ahead of time, so that I can do a numerical solution. So anyway, we'll do that, hit enter, see what happens, and here is the response of the system. Notice that before, when I excited it at the natural frequency, which is what I'm doing here, right? Remember, the original natural frequency was 1 radian per second. So my forcing term here is 1. Up here, when we did that, if you recall right here, for example, they grow and they just continue to grow. But now what's happening when you excite it at that natural frequency, you don't get an infinite amplitude. So what's happened is the absorber has absorbed the vibration from the original system, which is why they call it a vibration absorber. Okay, I have some videos that if I can pull up here, I will show. So they should be right in here. So let's shrink this down. All right, so this is coming from a professor who was also describing the vibration absorber. And the reason I like this web page is that he's got a nice little video here showing the effect of the vibration absorber. So the blue mass and blue spring is the original system. The red is the absorber that is attached. And what's happening, he doesn't, I guess that's what these arrows are for. The arrows are showing the forcing, the force that's applied to the blue. On the left-hand side, this is where the absorber is not tuned. And what that means is the frequency of the absorber is not equal to the natural frequency of the blue. Right? And on the right, it's the same thing. I believe that one of these has the red frequency below the blue's natural frequency, and this other one on the right, I believe, is where the red's frequency is above the natural frequency. You can see that, yeah, maybe it does something, but it doesn't do a lot. In this particular case, in the middle, this is where the absorber is matched to the natural frequency of the system. And at steady state, you can see that theoretically the original system sets still, and the red system is moving like crazy. You might ask yourself, how in the world does that happen? Well, you've got to remember, it will have a transient condition. And during that transient condition, the blue will in fact move. And as it moves, it will begin to push on the red and cause the red system to begin to vibrate. And then the transient will slowly, as the time constant dictates, will slowly, the transient will slowly disappear, leaving only the steady state. Well, by the time it gets to steady state, the red mass is already moving. And the red mass displacement will cause forces on the spring, which exert forces on the blue. And at steady state, the force in the spring, the red spring, will exactly balance the forcing term. Now, this is theoretical, because what will happen is in all real systems there will be some damping. And when you hit steady state, because of the damping, things will begin to try to slow down. And as the red one slows down, it no longer will be able to balance perfectly the blue, or the forces applied to the blue. And so the blue will, in real systems, move a little bit. But theoretically, if you really have no damping, when you get to steady state, then you'll have a blue sitting still. Of course, you might be thinking, well, if I have no damping in the system, it will take forever to get to steady state. So there is some limitations to the theory. But it does in fact work quite well. And so what I'll do is I'll show another video of something in real life. All right, so we'll come over here to an experiment that was done by some students. I don't recall exactly where they are. And so here's a building, model of a building, and they're moving the base like a earthquake might do, and you can see that it didn't move. Now they have this mass up here, which is their absorber attached to it. You can see that the building, even though the ground is shaking, the building is relatively stationary. It'll work a little bit because it's, like I said, the theory isn't perfect. And do these things actually, are they used in real life? Well, yes. Here's an example, and there's many more examples of a person who's attaching a vibration absorber to I think it's some type of building, and he derives his equations and shows you a picture of his absorber and that sort of thing. So yeah, these things are in fact used, like I said, the theory isn't perfect, but that's very typical of what happens. You establish some theory, and then you see what your limitations are. So anyway, let's go back to the Mathematica, and let me show you some other things that happen with this absorber. So here, what I would like to do is I'd like to calculate the theoretical steady state amplitude of the absorber equations. So what I'm doing is going in to get the transfer function between the absorber equations and the input. So if you look on the right, here are your equations, and convert these things into a transfer function. So you're going to end up with mass times s squared and x. And so here we go. Hopefully you can see where I've done that. So here's your x1 double dot, for example. Your x1. Here's your. So hopefully you can see that this is transfer function equations for the two equations that are shown over here on the right. And so then I just simply solve those equations, and I say it's the transfer function almost, because if you look at this, here's the two solutions. One's here and the other one is here. They still have the input over on the right hand side. So to get the transfer function, you have to divide by the input, right? So in this case you would divide by f0. Alright, so that's why I say, well, it's almost the transfer function because I haven't divided by the input. Alright, so anyway, there are two outputs in this case. There's x1 and there's x2, right? So that's kind of what you expect. It's 2 degrees of freedom. What you would want to focus on as the engineers, what are you interested in? And usually people are concerned about the response of the original system, so that would be x1. So I'm going to focus in on x1 as well. Alright, so what I do is I set f0, I forget, I had to tell Mathematica to forget about what f0 is, because I've set some values above when I was doing plots. But anyway, so I'm going to find the transfer function at a frequency, and all I'm doing is taking, this allows me to not have to copy and paste so much. But what I'm doing is everywhere I see an S, I'm going to plug in I times the forcing frequency. So in this case, I'm going to force it at a frequency of 2, which is not at the natural frequency. But anyway, we get the, like I've done before, I'm going to get the absolute value of the transfer function at frequency, and then I'm also going to find the angle at that frequency. Oops. Okay, I guess I didn't execute this one here. So let's execute it. Now let's see what happens to us. Okay. So in this particular case, I have a absolute value. So I have a magnitude at steady state of 0.375. That's when you're shaking it at twice the natural frequency of the original system. What I'd like to point out is if I shake it at 1, the frequency of 1. This means I'm shaking it at the natural frequency of the original system. I execute the same thing, and what happens is, right here, the absolute value, that's the magnitude of the steady state output, is equal to 0. So in other words, what I'm saying is, if you have theoretically, if you have the absorber tuned to the frequency, the natural frequency, your output amplitude is equal to 0. If you like, you can also calculate the frequency of the Xtube. So, what's the magnitude of the absorber? So I'm just going to put an Xtube in here. Execute it. Well, the absorber is moving, right? As you saw in the video from the other professor. But the original, the building or whatever it is that you're trying to absorb the vibration of, that has an amplitude of 0 right here. Also, you might find it interesting to look at the angle. This is how you would find the angle using Mathematica. It's fairly simple. You just simply say, I want the inverse tangent of, it's actually the imaginary divided by the real. For whatever reason, Mathematica, when it does an inverse tangent, the first argument is the denominator, and the second argument is the numerator. So it's the imaginary term divided by the real term of the transfer function, and then I just turn it into degrees. So if you happen to be below the natural frequency, then it moves, and you have an angle of 0. So what's happening is, and this is when it has no damping. So what's happening is it's in phase. So when the input peaks, so does the output. It peaks as well. If you get above the natural frequency, then your angle is 180, and you've probably seen that with the paddleball games. When you're hitting a ball that's connected to your paddle with a rubber band, the ball reaches its furthest extent when the paddle is back. Its furthest extent. They come together and they hit each other. So it's out of phase by 180 degrees at the natural frequency. Again, you find out that the angle is equal to 0. So it's in phase when it's at that. Okay, so that's a vibration absorber. I think I've shown you how to draw free body diagrams, get the steady state values, and all that sort of thing. Again, the limitation of these values is when you're doing these calculations, these are the values when you get to steady state. If you have no damping in the system, it will take you forever to get to steady state. So in the real world, if you really had no damping, you won't really see the 0 vibration of the original system, because you'll never get to steady state because there's no damping. If you add damping, then it will, the equations will show you that it's not perfectly 0. So I believe I have a place for some damping here, so we'll put in a small amount of damping. So maybe I don't know, let's do 0.1 because I want to emphasize the difference. So here we go. There's the equations when they have damping, and here is the solution when they have damping. And then we'll find the magnitude of these at the frequency, and you can see that it's no longer 0. It's actually got an amplitude of 1.6. So you add damping, it will not theoretically be 0. It'll be smaller typically, but not 0. But at least you do get to a steady state. So that's it. That's a vibration absorber. I'll post this recording as soon as I edit it a little bit.